Welcome to the deep dive. Today we're heading to Mars. Now, when you picture Mars, you probably think red dust, craters, maybe Olympus Mons, but picture this. Strange formations, almost like thick honey streams, just stopped, frozen on slopes and in craters.
Yeah, really evocative imagery. And for the longest time, scientists figured, well, these things must be mostly rock. Dust, gravel, maybe a little bit of ice, but nothing significant, just sort of dirty glaciers.
Right, not exactly a reservoir you'd plan a mission around. But okay, let's unpack this because some new research has dropped and it's pretty dramatic. It really shifts things.
It does.
So our mission today is to explore this. How does this revelation change how we see Mars's past, its climate history, and maybe more excitingly, what does it mean for humans actually going there?
It's a big shift from mostly rock to potentially, well, a lifeline. It really is a classic case, how initial ideas based on, well, limited data can just get completely flipped. Those honey streams, planetary scientists have always been curious. But the real story was hidden.
Hidden how? Just under the dust.
Pretty much, yeah. Beneath that dusty layer. And earlier studies, they were all over the place. Different teams, different methods, different locations. Some glaciers only partly studied, others not at all.
Ah, so no consistency.
None. It made getting a clear planet-wide picture impossible. So the assumption stuck. Mostly rock. We just couldn't reliably see inside.
So it wasn't just missing data, it was mismatched data, like pieces from different puzzles.
Exactly. You couldn't build a coherent picture.
Okay, but the sources mention a breakthrough. Yuval Steinberg, Oded Aronson, Isaac Smith, they developed a new method.
Yes, and that was the key. A standardized method. Finally, a way to compare apples to apples,
How did they do it? What was different?
They used data from SHARAD. That's an instrument on NASA's Mars Reconnaissance Orbiter. Think of it like radar that can penetrate the ground from orbit. It sends radio waves down.
And listens for the echoes.
Exactly. It can see a few hundred meters down. And to figure out if it's rock or ice, they looked at two things. First, the dielectric property. Basically, how easily radio waves pass through. Ice is pretty transparent to radar.
Okay.
Rock, not so much. It kind of blocks or scatters the waves more.
And the second thing?
The loss tangent. That's about how much energy the material absorbs from the wave. Like shining a light through clear water versus murky water. The murky water eats more light.
Got it. So clear ice lets waves pass easily and doesn't absorb much energy, while rock hinders them and absorbs more.
Precisely. By measuring those two signatures very carefully, they could calculate the ice-to-rock ratio beneath the dust. Far more accurate than just looking at the surface.
That's clever. It's like giving the glaciers an MRI scan from space. And they didn't just do this once, right? They looked at multiple sites.
5 different glaciers, yeah. Across both hemispheres, spanning different types of terrain.
And what did they find? Were they all different, or?
That was the really astonishing part. They were surprisingly similar.
Similar. Across the whole planet.
Strikingly similar properties. Doesn't matter if it was north, south, in a crater, on a mountain. The composition was consistent. It means we're not looking at isolated quirks. Isaac Smith, one of the authors, said it tells us the formation process, the preservation. It's probably the same everywhere.
Wow. Okay, that changes things. So these aren't just weird ice patches. They're part of a global system, a pattern.
Yes, a consistent planet-wide phenomenon.
And that consistency, that must tell us something huge about Mars's climate history, right?
Oh.
How could these massive, similar ice deposits form all over?
Exactly. It points towards consistent global conditions occurring repeatedly, not just a one-off ice age.
Yeah.
It gives us better clues about Mars's axial tilt cycles, how its tilt might have changed over millions of years, driving climate shifts.
Like Earth's ice ages, but driven by tilt changes.
Potentially, yes. And maybe hints about its lost atmosphere, how it might have once trapped enough warmth or pressure for this much ice to build up and stay stable. These glaciers, they're like time capsules. Each layer records a climate period, and their similarity suggests surprisingly stable cycles in the past.
So a more dynamic past than we maybe thought. Cycles of glaciation.
A much more dynamic and perhaps cyclical climate history, yeah. It helps us trace the path from a potentially wetter, warmer Mars to the cold desert we see now.
It's like finding matching historical records in different archives, all telling the same basic story. That consistency builds a really strong case.
It really does. It moves us from scattered observations to a cohesive planetary narrative.
That must be incredibly rewarding for the scientists involved.
Absolutely. But beyond the history, beyond the science of Mars itself, this has huge practical implications for us.
Right. The future. Human exploration.
Exactly. If we're serious about sending astronauts for long stays, maybe even building a base, Water is everything. You need it to drink, obviously. You need it to make breathable oxygen. And you can crack it into hydrogen and oxygen for rocket fuel.
And before this, the thinking was, what? Haul it all from Earth?
Either haul it, which is incredibly expensive and limits mission scope, or try to bake it out of the soil in tiny amounts.
Which sounds complex and energy hungry.
Very. Dealing with Martian soil, the chlorates purification, it's a huge challenge for small returns.
But now, knowing these glaciers aren't just dirty rocks, but actually rich in ice.
Rich is putting it mildly. The analysis shows a minimum purity of over 80% ice. 80%.
80, that's practically a water reservoir just sitting there.
Essentially, yes.
Yeah.
Vast, naturally occurring ice mines. It transforms them from geological features into critical resources.
So instead of searching for scraps of water, we found reserves.
Massive reserves. It changes the whole mission architecture. Bigger crews, maybe. Longer stays, definitely possible. Less reliance on Earth's supplies, hugely important.
It shifts the thinking from just visiting Mars to potentially actually sustaining a presence there.
That's the potential game changer, yes.
Yeah.
Living off the land, or in situ resource utilization, as NASA calls it, this makes it look much more feasible.
Okay, it sounds amazing, but are there catches? Like, is this ice easy to get to and use? Or is it still a big technological leap?
Oh, absolutely, there are challenges. Excellent point. Knowing it's there is one thing. Getting it out and using it is another. We need robots that can dig in ice in low gravity and extreme cold.
Right.
We need efficient systems to melt it, purify it. Even 80% ice means 20% something else, and then electrolyze it for oxygen and fuel.
So significant engineering hurdles remain.
Definitely. Working in that environment.
Okay.
The cold, the low pressure, it's tough.
Mm-hmm.
But crucially, now we know the resource is worth developing that technology for. The scale and purity make the investment make sense. We know what we're aiming for.
It really is incredible. A fundamental discovery about Mars's deep past, directly enabling our future ambitions. From dusty rock to over 80% pure ice. And using that clever radar technique, seeing beneath the surface, finding this consistency across the whole planet.
The consistency is key.
These glaciers are suddenly not just interesting geology, they're potential fuel depots, water wells, air factories. Vital for humans on Mars.
And if you zoom out, connect this to the even bigger picture. These aren't just resources, they're storytellers. Silent witnesses to Mars's entire climate journey, its lost atmosphere, its potential for ancient life. Did Mars ever have habitat sustained by this water?
Could it again?
That's the deeper question, isn't it? Their composition helps us model Mars's past environments, maybe even pinpoint times when life could have existed. And the researchers are already planning to look at more glaciers, build up that global picture even further, sharpen the focus.
More data points for the story.
Exactly. Each one adds detail. How did they form? How long have they really been there? How best could future explorers tap into them? Which I think leaves a really important question for you, for everyone listening. What other secrets are locked away in these ancient ice sheets? Secrets about Mars, sure, but maybe also clues for humanity's own future, out there among the stars.
A foundational lifeline, potentially. It certainly makes Mars feel a little less alien, a little more within reach. And on that thought, we encourage you to keep exploring the Red Planet and all the wonders science uncovers. Thanks for joining us on this deep dive. We'll see you next time.
For the complete news, visit our website. Support us by following and sharing.